Okay, excellent. Okay, I'm going to start. I'm not going to follow the sheet religiously, but I am going to start with the first topic. I'm going to start with radioactive decay. And what I'm going to begin with is an example that's not on the sheet, but one which I think is particularly nice. So I'm going to have two radioactive isotopes. I'm going to have radioactive isotope A, and at time 0, I'm going to have M0 of part of material A. This material is going to decay with a decay constant of K into material B. And at time 0, I'm going to have no material B. Okay. And then material B, when it does decay, is going to decay with another decay constant, which I'll call U. And then this will decay into a radioactive isotope C, which is no longer radioactive, but is stable. And my question is going to be, how much of each isotope is there at time t? So what we really need to do is write down differential equations for each of the amounts of the different isotopes. So can anybody in the chat? I'm going to try and start my video. Oh yeah, my video has started. Hello, everybody. I'm going to take suggestions from the chat. Can anyone give me a differential equation satisfied by the rate of change of the amount of isotope A? So can anyone suggest in the chat an expression for dA by dt? So this should be familiar. So we've got a decay constant of K. We know that for radioactive decay, the amount of a material, the rate of decay is proportional to the amount of material that's there. Okay, the intuition for that is if you double the number of atoms, you double the number of things which in any time interval might decay. So if you tossed, if you consider like a radioactive decay to be like a coin landing heads, if you tossed 10 coins, you'd expect 5 heads. If you tossed 100 coins, you'd expect 50 heads. You'd expect the number of decays to be proportional to the number of coins. So dA by dt is minus Ka. Right. Now, a test to see if people are listening and awake. Can anyone suggest a differential equation satisfied by material B? So material B is interesting, right? Because it's not just simple decay. There's two things which are happening. Material B is being produced by the decay of material A. So we've got a flow sort of into new material B. Now we know what that term is because we've already seen it. Okay, that term is the same as the decay of of material A. So we've got Ka coming in to being material B. But at the same time, material B is decaying. So we've got a flow out of material B of a term which is proportional to the amount of B, and the constant of proportionality is this decay constant Q. So we've got dB by dt is equal to minus QB plus Ka. And finally, dC by dt, well, this decay of B So the rate at which B decays is the rate at which material C is being produced because the decaying B is turning into C. So dC by dt is QB. Okay. If you add all of these three terms up, everything cancels. So we get d by dt of A plus B plus C is equal to 0. And that's just some, you know, physicists love conservation laws. That's like the conservation of, I don't know, mass number, sort of, I'm not of nucleotides, of sort of protons and neutrons. So that's that conservation law. So that all checks out. Right. How do we now go about solving this system of differential equations? So there should be leaping out at you a differential equation amongst these, which should be easy to solve. So let's see if anyone is awake, alert, listening. Which differential equation can I just solve for straight away, pretty much for free? Right, someone suggested dC by dt. The only problem with the dC by dt equation is it relies on me knowing B. It relies on me knowing how much of particle B there is. Great. There's some suggestions in the chat for dA by dt. Okay. Now, dA by dt is a differential equation you should just know the answer to. Okay. If you didn't know the answer to it, you can get it by separating the variables, by writing 1 over A dA is equal to negative K dt. That's just formally treating that differential fraction like a fraction and sort of separating the variables. What I've written down so far doesn't really make any sense, but it does if I wrap both things with an integral sign. And then if I integrate, I get the natural log of A is equal to minus K t. I need to put a constant in somewhere, and the most natural place to put a constant in is normally inside the logarithm, because then that just sort of sorts out stuff with signs. And then if I exponentiate both sides, I get CA is equal to e to the minus KT. If I divide by C and then fit my initial condition that the initial mass is M0, we just get that A, I'll call it A0 because then that's a little bit more consistent, is A0 e to the minus KT. And you should all recognize this as the equation for radioactive decay. So this is just my classic radioactive decay. So it just decays by an exponential function, and I can find things like the half-life. Yeah. So if I wanted to solve A is equal to A0 over 2, I would want e to the minus KT to equal a half. And so then if I take logarithms of both sides, I would get minus KT is equal to natural log of a half, which simplifies to the half-life being natural log of 2 over K. So I can relate the decay constant. So I can relate the decay constant K to the half-life. Okay, and notice that it checks out that if K is large, so if the material is decaying, quickly, then the half-life is short. Okay, so how much of each isotope is there? So far, I know how to find how much of isotope A. Okay, is everybody with me so far? If so, put a thumbs up into the chat. If not, put your question in now. Good, and we've got thumbs up. Yeah, we've got thumbs up coming in now. So now, I'm now in a position where I'm able to solve the second equation, dB by dt is equal to minus QB plus K plus KA. Because I now know an expression for A. So I can now use this expression for A in my second differential equation. So I've got dB by dt is equal to minus QB plus A0K e to the minus KT. And all I've done is I've replaced this A here in my differential equation for dB by dt by the highlighted expression I've got here for A. So what I've written down is just an expression for minus QB plus KA. So I now need to solve dB by dt plus QB is equal to A0 K e to the minus KT. Okay, so does anybody have any suggestions, any ideas of how to solve this, differential equation? Now, you may well not, okay? In which case I can show you some intuition about how to solve it. But does anyone want to in the chat give a suggestion for how to solve this differential equation? Excellent. Integrating factor would be the best approach. So the integrating factor would be to multiply both sides by e to the qt. Okay, so let's multiply both sides by e to the qt. So we get e to the qt dB by dt plus q e to the qt b is equal to A0 K e to the q minus k t. The beauty of this approach is that this left-hand side I can think of as this. I can think of it as e to the qt times dB dt. Then q e to the qt I can think of as the derivative with respect to time of e to the qt multiplied by b. And by the product rule, this whole thing is the derivative with respect to time of the product of e to the qt and b. And this is equal to A0 K e to the q minus kt. Okay, sanity check to check that everyone is following. What do I do now? I've got on the left-hand side, I've got an expression for a derivative. What do I do next in order to sort of undo that differentiation and enable me to find an expression for b? Great, integrate both. So I want to integrate both sides with respect to t. So if I integrate both sides with respect to t, I've got e to the qtb is equal to the integral of A0 K e to the q minus k t dt. Now, this is a good test to see if people have got a sort of eye for detail. When do I need to be worried about the right-hand side? So the right-hand integral does actually break down into two cases. So it's tempting just to say, right, I recognize this, it's an exponential function. So it's just going to be a naught k e to the q minus kt over q minus k plus some constant, which I'll call c. When do I need to be a little bit worried? When isn't this expression quite right? When there's another function of t? No, that's not the problem. Which term in this expression, and this is the sort of thing which, so you go deeper into physics, deeper into maths, you need to look out for these, like what I would call edge cases. Which term in this expression is potentially problematic? Yeah, what's potentially problematic is if I'm dividing, if q is equal to k, then I'm dividing by 0. Okay, and I would get an expression. I would get an expression that doesn't make sense. Obviously, in some sense, everything would, if q equals k, it's actually much easier because I don't get an exponential at all. I just get a constant, and I get e to the qtb is equal to a naught kt plus some constant c. I'm going to ignore that case because that case isn't particularly interesting, because that's when material A kind of just decays into something which is almost sort of identical to it. So I'm just going to leave that case. What I do need to do is I do need to find the value of c. So I do need to find the constant of integration, but I can find that by remembering that in my initial conditions, I start off with no b. So b is produced only when A starts decaying. So we get, I can fit initial conditions that when t equals 0, b equals 0. So I want 0 to equal to c plus a naught k over q minus k. So I just get c is negative a naught k over q minus k. Okay, and now if I divide by e to the qt, I get the following, that b is a naught k over q minus k e to the minus kt minus e to the minus qt. Okay. And physicists, scientists, okay, this is my sort of analytic solution. So this is my function. Would you really feel, what would be your instinct to do next to really sort of kind of to really convince yourself that you've not just sort of solved this mathematically to get mathematical symbols, but what would your instinct be to do next to really understand what's going on here? Let's imagine you were writing a research paper, you were investigating this. There's a strong case for saying that just solving the differential equation just gives you a formula. but does this formula really make much sense? Well, I would only really feel that I've understood this formula at the point where I could graph it. Okay. So, and I'll leave this as a sort of exercise to do, after the webinar. But I hope lots of you have played around with things like Desmos. And in Desmos, you can absolutely just create the, oops. So you can absolutely just create the function that I've just created. I need to make sure that I've got it around the right way. I think it's this way around. Okay, and ignore the negative axis. But hopefully this corresponds to the sort of dynamics that you would expect of this differential equation. So you would expect to see an initial period where radioactive isotope B increases in quantity, and it increases in quantity as A decays. But then eventually you sort of start to run out of A, and then you just run into eventually no new B is produced, and then it just tails off. You can change the two decay constants. So if you make radioactive isotope B decay faster, then you get less, you sort of build up less of it. If you make radioactive isotope Q decay really slowly, so you put the radioactive isotope B decay really slowly, so you make Q small, you get this much slower tailing off. And if you make K really big, essentially what happens is A turns into B really quickly, and then B tails off slowly. And when you do sort of real research and real work in differential equations, you probably spend a lot of time using a computer to sort of look often numerically at the graph and to try and sort of understand the dynamics as those parameters change. So in here, the two parameters are K and Q. So that was a little example that I had prepared that I thought might interest you of two-stage radioactive decay. So if you're happy with that, just put a thumbs up into the chat. If not, ask any questions that you might have. Great, we've got thumbs up. Right, that was something which I had prepared as a little sort of extension from the sheet. What I will do now is, if people want to take requests, if there's any questions from the sheet that people would like me to go, if there's any particular questions from the sheet that people would like me to go through. Were there any questions that people wanted me to go through from the sheet? No. Okay. Would people like, I'll put it to a vote then. Would people like me to, next up, to go through one of the questions from the sheet, or would they like me to do another example like this, which is a little bit of kind of extension? Another example. Oh, brilliant. Okay, that's sort of everyone's I like everybody. Everyone's asked for extension. Good. That's what I'm keen to do as well. So if there are questions from the sheet you want me to go over, then do let me know. The next example I will go through is there's a little story. There's a little story attached to this one, and it will actually take us to something which I think is quite interesting about the dynamics of differential equations. So the story starts with an ocean. And what I'm going to imagine is that we've just got a lovely ocean, which is full of sea life and seaweed and, you know, all sorts of sort of nutrients for animals. But at the moment, no predators, so no sharks, and also no fish. Okay. And what I'm going to introduce is at time 0 into my sort of full abundant ocean, a small number of breeding pairs of fish. So what would be the most simplistic differential equation model for the growth in the number of fish? What would be the differential equation number 1 that you might write down? So you might argue that, right, new fish are babies. So if you've got one set of breeding pairs, they might produce, I don't know, 10 live offspring. And then if you had 2 sets of breeding pairs, they would also produce 10 live offspring. So the amount of offspring proportional to the amount of breeding pairs. So the first differential equation that you might write down is dp by dt is equal to kp, and then some initial conditions. Okay. Now, pub quiz question: what model of population growth is this? What would the solution look like? What do we call this differential equation? Yeah, exponential. Brilliant. Okay. Next question. Exponential growth, we know, looks like this. And in the short term, that seems likely. But why would sort of unfettered exponential growth not be a good model in the long term? What would happen if you just let exponential growth grow and grow and grow and grow and grow and grow? Well, what you would expect is actually in the real world resources to become more scarce. And if the ocean became really, really full of fish, you'd expect it to become more competitive for every fish that's born in order to survive. So breeding pairs of parents might not have 10 live offspring. It might start to decay to 7 or to 6. Eventually, it could just hit a critical point where 2 parents only have on average 2 live offspring, where you get a constant population. So what we'd want to factor into our differential model is a term that took into account the amount of resources. Okay, so how many resources are available? Well, that obviously decreases as a function of the amount of fish. So what I can introduce is an extra term and I'll call it P minus P infinity. So P infinity is the sort of limiting population. Oh, I mean it the other way around, sorry. P infinity minus P. So as P increases, intuition test. What I'm going to try and do actually is I'm just going to try and set up a collaborative whiteboard. This might all go wrong, but what I'd like you to do on the collaborative whiteboard when I set it up is draw, you won't have time to solve it, but draw what you think the solution to this differential equation will look like. So I'm going to try that. So I'm going to try and set up a collaborative whiteboard. This might all go wrong. So let's do a whiteboard. Okay, so I've got a whiteboard. Can people write on this? Yeah, super. Well done, Paris. Okay. I'm always keen to experiment with new things. So here's our differential equation. And oops, I'm unable to write on it. So, but the differential equation was dp by dt is equal to kp, and then we had this p infinity minus p term. Does anybody want to just sketch what they think it's going to look like? Oh, ooh, an oscillation is okay. A very good suggestion. Okay, I'm going to try and convince you that it's not I'm going to try and convince you that it's not an oscillation in a moment. And I'll actually show you not a technique for solving differential equations, but a technique for visualizing them. Oh, right, Edith's drawn something nice. She's drawn a curve that looks like that. Well done, Edith. And I'm now going to try and convince people that Edith's got the right idea. So I'm going to move away from my whiteboard and go back to my OneNote. Oh, wow. So what can people see at the moment? Can people see my OneNote? Yes, excellent. Right. What I'm going to do is I'm going to try and convince people that Edith had the right picture. And what I'm going to do first is I'm just going to consider this expression Kp P infinity minus P. Okay, and I'm just going to draw this on a sort of axis. And I'm only going to draw it for positive P because negative population doesn't make any sense. So it's obviously a parabola, and it's 0 at 0 and P infinity. And then it's maximum at P infinity over 2, and then it becomes negative. So let's remind ourselves that this graph is a graph that shows the gradient for different values of P. Okay, so I'm now going to consider what happens to the population against time. So my y-axis is P for population. My x-axis is T for time. Now, if the population is 0, I can see that my derivative, p infinity minus p, is also 0. So if the population was 0, the gradient of the graph would be 0. And so what I can do is I can just say that if the population was 0, the graph would be flat. So I'm just going to draw lots of flat lines. As the population increases, however, the value of this dp by dt function, so the value of the gradient on the right, increases. So that means that for a higher population, the graph is going up at some positive gradient. And in this region, it's getting steeper. At p infinity over 2, we have the steepest gradient of all. Because dp by dt is biggest. And then as the population increases past p infinity over 2, it becomes less steep again. And it's sort of symmetric. And then eventually at p infinity, so at here, the gradient is just 0 again. And above p infinity, the gradient is negative, and the higher you are, the more negative it is. So what we can do now is we can think about different solution families. So if my population starts here, starts small, the gradient to begin with is small. Then it increases as the population increases. So that corresponds to this graph going up. It then goes up more and more steeply until it's got a maximum gradient here at p infinity over 2. It then obviously has got a positive gradient there, so it increases past p infinity over 2. But as it increases past p infinity over 2, it starts to get less steep, and then it gets less and less steep until it gets, if it were to reach p infinity, it would become completely flat. But what actually happens is it just becomes less and less steep, and it just approaches an asymptote at p infinity. Okay, Paris's idea about oscillations is not a bad one. And maybe in the real world that would happen. And certainly with predator-prey models, it certainly does. But I think, although Paris's intuition about oscillations was wrong and Edith's curve was correct, what Paris had right is that you can get a decreasing population, because what we can see here is if we force the population to go past p infinity, so if we stuck in too many fish, the gradient function would become negative, and so the fish population would come back down. And if we're a long way above p infinity, it's going to come down quickly, and then it's going to come down more and more slowly. So this p infinity is then equilibrium. Okay, a little bugbear of mine, I think that A-level maths too much teaches you purely the formal process of integrating functions to get a formula for the solution, and doesn't do enough to get you to build up intuition around differential equations the way I've just done here. Because arguably, understanding that this is what the differential equation sort of looks like, is more important than what I'm going to do next, which is just find the equation of the population. But that's also I'm not saying that's not an important skill, so I'm going to do that next. So Let's now think about how we would solve the differential equation dp by dt is equal to AP p infinity minus p. Suggestions, people. What's the process by which I can solve this differential equation? So the first thing I want to do is I want to get all the p's, separate the variables. Good. I want to get all the p's on one side. So I just treat everything like a fraction. And I put every term with a p on one side and every term without a p on the other side. This makes no sense, but it will make sense if I just wrap everything in an integral. Right. Suggestions for how to integrate here. Okay, in the chat, partial fractions, excellent. Okay, so let's try and split it into partial fractions. So we want constants a and b okay, well, if I just make a and b equal to 1, this would have the right denominator, but would be p infinity minus p plus p, which would just be p infinity. So I could write this as 1 over p infinity is equal to minus k et. Okay, I think I'm happy with that. So we can now integrate the integral of 1 over p in the chat, please, to see if you're awake. Excellent. It's natural log of p because it's just function on the bottom and its derivative on the top. P infinity minus p, that's also like a natural logarithm, but the sign is wrong. So we've got minus log p infinity minus p. And this is minus k t. And then if I just I can take the factor of p infinity over to the other side. And I get minus k p infinity t. I might sometimes, if you just get these sort of multiple constants, it's just a nice idea to wrap them up as one constant. So I might call k p infinity a new constant like r in a bit, because I'm just going to get bored of writing it. The logarithm on the left, I can use my law of logs. But what I should remember is I do need a constant of integration. So I'll put that in now. And the best place to, if there's logs flying around, the best place to put the constant of integration is inside the logarithm. So I'm going to write it as, I'm going to put my constant of integration there. And I am going to do what I said before. I'm going to call k p infinity. I'm just going to call that minus rt. And then I exponentiate. So I get cp p infinity minus p is equal to e to the minus rt. When t equals 0, well, I'll find c later. So I now want to rearrange to find p. So I can write cp is p infinity e to the minus rt minus p e to the minus rt. So then I get c plus e to the minus rt P is equal to, whoops, my pen has stopped writing. Oh, is this nonsense? Sorry, I'm just going to close OneNote and reopen it. Okay, so I get C plus e to the minus RT. Oh, my pen has stopped working. This. I'm in the home straight, but my. Okay, I'm just going to have to write with my mouse for a second temporarily. So this is equal to P infinity e to the minus RT. And then if I divide, I get P is equal to P infinity e to the minus RT. And then I've got C plus e to the minus RT. And then this is equal to P infinity over, sorry, this is minus RT, 1 plus C e to the RT. Okay. And again, the best way to understand this function is to put it into Desmos or to some graphing package and to convince ourselves that it's got the right dynamics. So we had something like y equals P infinity, which I'll call the letter P. Oops. Over, and then it was 1 plus e to the RT. And I'll add all those sliders. Oh no, sorry. T should be X. Okay, and so there we've got, and there we've got exactly the type of function that that was suggested by Edith. Okay, so you can see that it's this characteristic function that is sort of exponential growth to begin with, and then tails towards a limit, and that limit is this equilibrium population. Okay, so that's a slightly more sophisticated population model. Okay, does anyone have any questions about that differential equation, or are people happy and keen for me to continue? If you're happy, put a thumbs up. If you've got any questions about what I've just done, please put them into the chat. Oh, double thumbs up. That's nice. Okay, I'm now going to go back to my OneNote, and I've certainly got my preference in mind for what I'm going to do next, but I will open it a little bit up to democracy. So I'm just going to show you the sheet just to remind you what was there, and then I'm going to ask you which type of question you'd most likely need to go through, and then I'll see if you've picked the right one. So let's go back to my OneNote. And so here's your problem sheet. So we've got examples from kinematic. We've got an example of an emptying container, drag and terminal velocity, nice questions about rockets. And then we've got damped and forced oscillations. Which of these topics would you like to see? Oscillations, good. I think that is the correct answer. Okay. Have you looked at, right, okay. So I'm going to look at the whole shebang. Okay. I'm going to look at damped oscillation. I'm going to look at forced damped oscillations. But what I'm a little bit concerned about is my stylus is not working. Okay, I'm just gonna close and reopen OneNote. Sorry. Oh, my whole touch screen's not working. Sorry, Vlad. Is Vlad still on the call? I think I might need to restart. I think I might need to restart my computer. Has Vlad made me host? Yes, he's made me host. Okay, I'm just gonna try and restart my computer and hope that gets the touch screen back working. I'll be back very shortly, hopefully, to go through oscillations. oops, I'm going to look at oscillations. Before we look at damped oscillations, let's have a look at undamped oscillations. So the most famous differential equation that you'll meet, or the most kind of important differential equation that you'll meet in physics is the simple harmonic oscillator. So we've just got x double dot is negative omega squared x. Okay, now I'm sure you all know the solution to this. Okay. Arguably, the best way to solve a differential equation like this is just to know the correct answer. Okay. So we're looking for a function which, when we differentiate it twice, gives me up to a constant the negative of the function. So if I was to just guess a solution, one solution could be a trig function. So I could guess, because I know it gives me an oscillation. And if I just differentiate cos of kt once, I get minus ak sine kt. If I differentiate it a second time, I get minus ak squared cos kt, which is minus k squared x. And to make it all work, I just need k to equal omega. So one possible solution is a cos omega t. And by exactly the same sort of calculus, I've also got a solution b sine omega t. I can choose a and b. I've got two constants there. I can choose a and b to get the initial displacement and the initial velocity right. And because we're sort of physicists rather than mathematicians here, we can just assume that if something satisfies the initial conditions, so the initial displacement and the initial speed are right, and the acceleration is right, we can assume that the displacement is correct. So that we can make this assumption that differential equations have got a unique solution. Okay, I won't prove that here, but that is something that you will prove in a maths degree, as long as the differential equations are sufficiently nice. Okay, and a linear differential equation like this is nice enough. Right, what I'm going to do now is, so I've got my oscillating system governed by this differential equation, and I'm going to add a force. And so we've got a sort of mass on a spring, and it's performing some sort of motion. And let's imagine that we introduce a force that is also periodic. Okay, and so I'm going to let the force that I introduce be, I'll put in an extra constant of m so that cancels when I use Newton's law, and then I'm going to call it F0 cos k t. Okay, so now my differential equation of motion is as it was before. So this term is coming from like the spring constant or the simple harmonic motion, but now I'm adding this extra driving force. And now if I divide by m, I want to solve this differential equation, x double dot plus omega squared x is equal to f naught cos kt. Okay, now there's a big idea here, and this idea, it's a little bit like sort of matrices, if you've seen matrices, or linear algebra, if you've seen linear algebra, is I can think of this differential equation on the left as being like an operator. Okay, so an operator is a sort of function that acts on functions. So if I give it a function x of time, I can differentiate that function twice and add it to omega squared times x. Now, in order to solve this differential equation, okay, I know that if I give the left-hand side a cos omega t plus b sine omega t, is just going to spit out 0. Because that's the solution of the differential equation when I've got 0 on the right-hand side. So if I could find, if I want to solve this differential equation, I just want to find one function that works. And then I can add on multiples of a cos omega t and b sine omega t. And that will, those, when I differentiate them twice and add omega squared times x, it'll just give me 0, and that won't affect the value. So can anybody suggest what type of function would end up giving me on the right hand? So if I set xt to be some function, what type of function, if I was to differentiate it twice and add omega squared times the function, would be a good candidate to give me something like f0 cos kt? Okay. As I might have said earlier, the best way to solve differential equations is often just to guess the correct answer. Well, if I want to get a cos kt term, a good function, the sort of function that's going to make a trigonometric function is going to be something like cos kt. Oh, and also, in order to solve the differential equation, I'm just going to assume that x of 0 and x dash of 0 are both 0. So I'm just starting my oscillating system from rest in equilibrium. Right, so I'm going to guess that my solution is going to be something like a cos omega t, cos kt. And let's see what happens. So x dash t is minus ak cos kt. X double dash t is minus ak squared cos kt. And then x double dash t plus omega squared x t is equal to a omega squared minus k squared cos kt. And that works as long as I choose a to be correct, as long as I choose a correctly. So as long as I choose a, so that a omega squared minus k squared is equal to f naught, it's right. So I need to put a as f naught omega squared minus k squared. So that is what I call a particular integral. So this function, xt, is equal to f naught cos kt over omega squared minus k squared. That is a possible solution, but it can't be the solution that I want because it doesn't have the right initial conditions, because it doesn't start from rest, because it's a cos wave. It does start with 0 velocity, but it's not starting at equilibrium. So in order to get something which starts in equilibrium, I need to add my sort of general solutions, my things which go to 0. So I can add a lots of cos omega t and b lots of sine omega t. And now I need to choose it so that it starts initially at in equilibrium at rest. So x0 is f naught over omega squared minus k squared plus a. So I just want a, to make that 0, I want a to be minus f naught over omega squared minus k squared. So I get my solution is xt is equal to f naught omega squared minus k squared cos kt minus cos omega t plus b sine omega t. But if I make the initial velocity 0, when I differentiate, the coses goes to sines, the sine here goes to a cos, and then when I plug in t equals 0, the only term I get is the b cos omega t, and when I set that to 0, I get that b is 0, so this term goes away. Okay, so this is the solution to an undamped spring with an oscillatory force. Okay, so you can imagine this being modeled in the park. Okay, on the swing, every child loves going on the swing. So what you could model this by is my daughter's on the swing, okay, and I'm pushing her rhythmically, okay, according to some cos wave. Okay, so I've got a time period of pushing and pulling, pushing and pulling, pushing and pulling, pushing and pulling, and that has got an angle, that my oscillatory pushing has got a period of a sort of angular velocity of k. The natural mode of the swing, so what the swing would swing at if I didn't push, has got an angular velocity of omega. Okay, what we've done here is we've solved the maths. Okay, so we've got an equation for this forced oscillation. Really want to, and I've made this point several times, is that solving the maths is great, but it doesn't correspond to understanding. So what I'd like you to put in the chat, actually, yeah, I'm going to try this thing with the whiteboard again. Well, either explain in the chat, describe what you think you would get, or on the whiteboard, have a draw of what you think this would look like of cos kt minus cos omega t. Okay, so put on your physicist's intuition or your mathematical intuition, and you can either think of it in terms of the graphs, or you can think about what would happen with me pushing my daughter on the swing. Okay, so let's try this again. So, make it a little bit interactive. Let's go. I'm going to go back and put the whiteboard in. Are we going to get any suggestions on the whiteboard or in the chat of what happens? It's a harder question. No. Okay, what I'm going to share. Actually, can I just ask people? I'm going to check people are still there and listening. Can people just put a thumbs up if they're happy with what I did just up to now to get that to get this solution for the forced damped. So this is my forced undamped oscillator. Okay, great. Polar's still there. A few people are still here. Great. Right, what I'm going to... Okay, people are saying in the chat that they get the maths, but they're finding the graphing tricky. Okay, so what I'm going to do, I'm just going to ignore the amplitude of the wave for the moment. Okay. Oh, so someone said, why did we throw away B sine omega t? Yeah, I did gloss over that a little bit because I just got a little bit lazy. I set up as my initial conditions that the displacement was going to be initially 0 and the velocity was going to be initially 0. So when I got to here, I've got two cos waves and one sine wave. The only thing which is going to contribute to a velocity at time 0 is the sine wave, but because the velocity at time 0 is 0, b must be 0. So that's why we lost that term. The multiple of the cos wave from the general solution was minus the amplitude of the cos wave in the particular integral, so that we had initially the particle being at equilibrium, initial displacement being 0. Right, what I'm going to do now is I'm going to go back and share some Desmos, and we're going to do this graph sketching, and we're going to try and figure out what's going on. So oops. So I'm going to stop share, and now I'm going to share, and I want to share, where's my Desmos? I need to create Desmos again. I think I lost it. So what I'm going to do is I'm going to just look at the waves, and so I'm going to plot cos of kx minus cos of wx. I'm going to add sliders, and I'm just going to put w and k to be different for the moment. Okay, so what we get is we get a little bit like a kind of heartbeat. Okay, so I'm just going to change my w. So let's change it to 3. And what we see is we get a sort of rather complicated oscillation. So let's do 1.1. And what you can see is you get a little sort of wave here where the amplitude kind of increases, and then the amplitude decreases. And then if you keep doing it over time, you get something like a sort of heartbeat where that little wave packet sort of repeats. So you can see these little repeating wave packets. If I put K and W very close, you can see that you get this sort of longer drawn out heartbeat. Okay, so there. Can I change I want to change like the Y scale. So I just want I want the Y scale to be on a sort of different order of magnitude to the X scale, so that it doesn't there we go, that's much better. Okay, so what we've got here, we can see that the amplitude increases and then it decreases. And then you get this sort of beat, you get this beat phenomenon. Okay, let's try and understand this from the perspective of the physics. So I'm going to go back to my OneNote. So what we've got here is we've got two cos waves which are of different frequencies. Now, what will happen is that sometimes the cos waves will be in phase. And when they are in phase and you subtract, you just get that the waves cancel. But over time, the cos waves, because they're progressing with a different angular frequency, the angular frequency is sometimes is in one K and in the other omega, because they progress with different angular frequencies, at a later point, they're not going to be in phase, they're going to be in antiphase. And when they're in antiphase and you subtract, you get reinforcement, so you get a bigger amplitude. Now, if you want to see this mathematically, you probably know that there's a formula for the difference between cos waves. You get cos kt minus cos omega t is 2, well, it's minus 2, and then it's sine k plus omega over 2 t sine of k minus omega over 2 t. And so what you get is that if k and w are close, this is just like a sine wave which has got approximately angular velocity of omega. So what you get, if I push the swing at something which is close to the angular velocity of the swing, so the natural frequency with which the swing oscillates, my daughter will go on the swing at that natural frequency. But you get a second term, which is a second sine wave. And that sine wave progresses with a angular velocity, which is like half the difference of those two waves. So this amplitude term has typically got a longer wavelength. So this is my sine k minus w over 2 over t term. So it's got a longer time period, not wavelength. So it's got something like this. And then my oscillation of my swing is going at the oscillation of natural frequency of the swing. So what you get is these you get this beat phenomenon. Okay. So if I'm not a particularly good father and I'm not pushing if I'm sort of not paying attention to how I'm pushing the swing, and I'm pushing it a little bit out of phase with the natural frequency of the swing, then I might start pushing my daughter in the right bit, in the right way. So pushing her when she's at the back of the swing and giving her more energy because I'm pushing in her direction. But if I'm not in rhythm, I will eventually be out of sync with the swing and be pulling when I should be pushing and pushing when I should be pulling. And then at that point, I'm just serving to slow her down, and then I end up stopping her. So what you get here, if you have forced oscillation, which is not in the same frequency as the oscillation with the swing, then you get this beat phenomenon. Now, what I haven't paid attention to yet, so I've got this beat phenomenon, but what I haven't paid attention to yet is this term, the f naught over omega squared minus k squared. And that is obviously it's going to be that's half the height of this wave, so the maximum amplitude. So this total amplitude here is 2 f naught over omega squared minus k squared. The f naught is kind of obvious. Okay. The f naught is how hard I push. So the harder I push my daughter, the bigger the swings that you would expect. But what does the denominator, being omega squared minus k squared, tell me? How else could I make the oscillations of my daughter big? So one way to make the oscillations big would be to make f naught big. But how else could I make, if you think about the denominator, put into the chat how else I could make the oscillations big. Well, the other way that I could make the oscillations big is by making the denominator small. Okay, but the denominator, omega squared minus k squared, is going to be small when k is approximately omega. So in other words, if my driving force of the swing, if I become a better daddy and I'm pushing better and I'm pushing more in the rhythm of the swing, then the amplitude of the oscillations get bigger and bigger. Okay, because then I'm more and more, at the time when I'm in phase for a long time. So if I go back to my Desmos, as well as the difference between the cos waves, what I also want is I also want to divide by, I want to divide by the whole thing. So I want cos kx minus cos omega x on the top. And then I want as my denominator, I want my amplitude to be omega squared minus k squared. And what we can see here, and now I do need to change the y scale. What I can see here is that when K and W are very close, I get very large oscillations. As K and W become different, the oscillations are small. But as I get close, as W becomes closer and closer to, I'll just change this to 0.9 to, oops, 0.9. Oh, I don't want, no, I want 0.9 to 1.3. So here, as I get closer and closer to 1, the oscillations get bigger and bigger and bigger. And the beats get wider and wider. And if I set W equal 1, something happens. But if I set W very close to 1, I get this. And if I just change my y-axis, my amplitude is just getting bigger and bigger and bigger and bigger and bigger and becoming huge. What do physicists call that effect? Yeah, resonance. Now, mathematically, if K was to equal W, okay, my guessed function here would actually just no longer work. And it turns out when you solve it mathematically that the function that you actually end up needing to put in is not just a constant times cos t. It turns out that the solution that you really need is something of the form t sine omega t. Okay, so this is clearly mapping. This has clearly got displacement 0 at time 0. If you differentiate it once, you get sine omega t plus omega t cos omega t. If you differentiate it twice, you get cos omega t. Ooh. W cos omega t. I'm rushing. Then you get minus omega squared t sine omega t. And then you get I think you get minus omega cos omega t, and these cancel. And then you can see that it satisfies the differential equation as well. So it turns out that the solution is actually xt is equal to t sine omega t. Turns out to be the actual mathematical solution. And we can see exactly what this is. And we saw shades of it in the Desmos, that what you get here, and this is what happens at the park if I push my daughter in exactly the right frequency, so the frequency the same as the natural frequency of the swing, I just get a sine wave, but the amplitude just gets bigger and bigger and bigger and shoots off to infinity. And that is resonance. Okay. Does anyone have any questions about that? The undamped forced oscillator. If not, put a thumbs up in the chat. Super. Okay, well, I hope that was a useful session. Okay, so we did some nice examples. We started by looking at two-stage radioactive decay. So radioactive decay via some intermediate isotope. And we got a nice differential equation. And we got a nice graph here that we then investigated via Desmos, and it gave me the right sort of dynamics. Notice that this is sort of similar to what we got at the end. Then we looked at this nice example of population growth with competing for resources. And we got away from we saw that population grew exponentially. And then as resources became scarce, it reached a plateau. And we saw this nice diagram, which you'll see again, which is called a phase plane, where we just thought about the gradient at different points. And then we looked at oscillations, and for oscillations, we focused on, where did I do the oscillations? It was up here somewhere. For oscillations, we looked at an undamped oscillator, so just a smooth swing, but with a forcing term. So Paris has asked, how did I combine those cos waves? You've probably seen the product formulas. So we know that sine A plus sine B, these are sort of trig identities that are just sort of a little bit on the fringe of A level. But we know that sine A plus sine B is sine A plus B over 2 cos A minus B over 2. Cos A plus cos B is 2 cos A plus B over 2 cos A minus B over 2. Okay, and what I looked at the one which is the difference between two cos waves. And you get, that's minus 2 sine A plus B over 2 sine A minus B over 2. Okay, you'll meet this again. So this is a really important, the reason these identities are really, really important is because these, for a physicist, these tell you what happens when two waves meet. Okay, and when two waves meet, you get two phenomena, you get a product of two waves. Okay, and what is quite typical is if two waves meet and they've got similar frequencies, let's just do it with the sine waves. You get one wave which has just got the average frequency of the two. But then you get a cos wave, which acts like the amplitude, which has got a frequency, which is the difference between the two. You might sometimes notice this effect if two people are tuning up a violin and they play the violin ever so slightly out of tune. So what you'll hear in terms of the frequency of the sound is essentially the note that they're both playing. But because the sounds are slightly out of phase, sometimes they reinforce to make a loud sound, and then sometimes they're out, disappear, so you get this beat phenomenon. Okay, and that beat phenomenon is exactly what you also get if you push your daughter on the swing and you're not pushing in complete, if you're not pushing in complete harmony. Okay, any further questions? People are saying they learned a lot, which is also nice. I really enjoyed it, giving this too. Oh, so people have just said, how does that map into an overarching sine functions with a cos function within? Let me just go back to my Desmos. Where's my Desmos? So here, I'll just make this I'll just make the omega a little bit closer to, a little bit further away. So here, you can see a red, if you look at the amplitude of the red bits, but if you zoom in, you can see that there's a kind of carrier wave. So there's a high frequency wave. So that's my daughter swinging. And then there's a low frequency beat, which is the beat of the amplitude. And that's the swings sometimes being big and sometimes being small. Okay, any more questions, or should we leave it there? Super. I think we'll leave it there. Hope everyone's enjoyed tonight. I hope that was useful and gave you a little bit of context for the sheet. As I say, I think it was a really, really good sheet. So hope you enjoyed the webinar, and I hope to see you all again soon. I'm getting thank yous coming through, which is always nice. Okay, good evening, everybody.